Okay, thank you. So my name is Oskar, and I will talk about our work in progress on partial evaluation of forward mode automatic differentiation. And this is work between myself, Viktor Palmkvist, and Broman. So forward mode AD is asymptotically efficient, but it requires a non-standard representation of the real numbers in the form of, for example, pairs encoding dual numbers. And this leads to a constant runtime overhead, as we cannot directly compile the elementary functions to cheap floating point operations. On the other hand, symbolic differentiation does not suffer from such runtime overhead, and it also allows us to do expression simplification at compile time. However, it is not as expressive as AD in the sense that we cannot always symbolically differentiate all expressions in more expressive languages, including general recursion and higher order functions, at least not at compile time. So the research challenge that we're addressing is how we can combine the strength of ST and AD while mitigating their weaknesses. So the key idea is to use partial evaluation of AD to combine the expressiveness of AD with the efficiency of ST. And this is an idea that has been proposed before in the literature. However, in contrast to previous work, we define a whole program transformation where we explicitly handle lifting and differentiation of free variables. From a high point of view, we can view our transformation as a pipeline where we have some input program that may contain some there constructs. And then we do a partial lifting of this source code. So we lift the parts that are affected by differentiation, possibly duplicate some code to avoid having to operate over dual numbers. Then we employ the standard forward mode AD transformation to generate code for computing derivatives. And then finally, we partially evaluate this generated code in order to sort of reduce the need to operate over these dual numbers. The key challenges when considering whole program transformation is that derivatives may contain free variables, in this case f, and we have to somehow lift these. We cannot simply substitute f for its definition before lifting, as this would generally lead to a code explosion. It may also be the case that f is used here both inside and outside a differentiated expression, and we don't really want to call f a lifted version of f outside of the differentiated expression, as it is associated with a higher runtime cost of operating over dual numbers compared to floating point numbers. So the key idea is to keep both a normal and a lifted version of f, which we call f hat. For left-bound expression, it's easy to add an additional version of f called f hat, but it's more challenging for higher order function, as the definition of f hat will depend on the place of application of this expression. Here instead we try to add an additional parameter f hat to this expression, and then we also have to update relevant parts, relevant places where we do the application of this expression. And the way we keep track of this is via propagation via the type system. There are still some unsolved challenges here with regards to transforming sum types and pairs. It's also the case that when we do the partial evaluation, when we encounter a free variable, sort of the partial evaluation halts, and their code is essentially similar to pure AD code. We can improve on this for scalar functions, for example, by instead of lifting f to f hat, a free variable f hat directly, we can lift it according to this relation where we essentially lift it with using itself and the free variable f prime, which denotes its derivative. And we can then construct the definition for this derivative f prime using the direct construct itself and the definition of f. And then we can generate efficient code for computing it by like recursively employing the transformation on this definition. There's also some standard challenges related to recursion when you do partial evaluation, such as code explosion and termination. And the idea here is to take a pragmatic approach where we sort of use a user-defined max recursion depth and basically unroll the recursion until that depth, and then leave the rest of the computation to the runtime. Okay, so that is it for me. You're welcome to join me at my poster if you have more questions.